Hello and welcome to Lesson 6.4, Applications of Vector Addition. Today we shall examine some various different forces that act on objects as represented by vectors, specifically when vectors are in a state of equilibrium. What I mean by state of equilibrium, let me show you an example. Let's say we have two vectors. I'm going to draw this vector and this one. So let's say we have this vector A and this vector B. What you'll notice is A plus B equals 0 vector. This is what we call a state of equilibrium. Also, if you had three vectors, let me draw three vectors here. So let's call this one P. I'll call this one Q. And I'll call this one R. Well, in this case, you can see P plus Q plus the vector R is also equal to the 0 vector. It goes back to where it began. So anything that adds up to the 0 vector is what we call a state of equilibrium. So Newton's first law of motion states an object will remain in a state of equilibrium, a state of either uniform motion or a state of rest, unless another outside force acts upon it. So a force that has an equal but opposite force to the resultant is called an equilibrant. So let me show you what I mean. So I'm going to find the resultant of this u plus v right here. I'm going to measure using my ruler again, trying to be as accurate as possible. So my resultant would be this vector here. This is my resultant. Whereas the equilibriant is the equal and opposite force. I'm going to draw it tail to tail with it. It's called this vector. This is the equilibrant. It's the exact same size as you can see, but headed in the opposite direction. Okay, so some things to note. The magnitude of a force is always measured in newtons. If we have any objects at a certain mass in kilograms at Earth's surface, we can use the approximation of 9.8 newtons acting upon that 1 kilogram mass. So 2 kilograms would be double 9.8 newtons. And we shall use our vector addition skills to combine vectors. Okay, so let's take a look at an example. For part A, find the magnitude and direction of a resultant force of 4 newtons and another force of 6 newtons acting at an angle of 20 degrees to each other. Okay, so we're going to draw an example of this. So this is going to be my 4 Newton force. Here's my 6 Newton force, and this is about 20 degrees to each other. Okay, so the resultant, let me draw using triangle law. And here's my resultant. I'm going to call it the vector R for resultant. So, what I'm going to do is I'm going to again use cosine law to help me out, but I need this angle down here. So 180 minus 20 is 160 degrees. And I know this is 4 newtons. So my resultant, that magnitude squared, is equal to 4 squared plus 6 squared minus 2 times 4 times 6 times cosine of 160 degrees. So again, make sure you show what you're substituting. Use your calculator. Don't have to show me all the steps here. Just make sure you're working it out properly. And I get about 9.9 newtons. You can round it to whatever you like technically. Just make sure you don't change the exact value in your calculator. Just store that somewhere. Now we're going to find the angle at the end near the 6 Newton force. I'm going to call this theta. So I'm going to use sine law. So sine theta over 4 is equal to sine of 160 degrees over about 9.9. So I'm going to put a dot above that equal sign, showing that it's approximation. So again, don't have to show me all the steps here. Just work it out. Something to note, please notice that this sine law is not an ambiguous case. If you forgot what an ambiguous case is, you may want to review that from grade 11 notes or grade 11 concepts. If it was an ambiguous case, you may have to take into account multiple options or multiple answers. But because it's not an ambiguous case, there's only one solution. This turns out to be 8 degrees, approximately. So therefore, what we can say is the resultant is about 9.9 newtons, 8 degrees from 6 newtons. Now, if we wanted to find the equilibrant force, how it compares to the resultant again is it's the exact same size. So the equilibrant is about 9.9 newtons. However, it's in the opposite direction. So it's not 8 degrees, it is 172 degrees from the 6 Newton force, because it's headed in the opposite direction. And 180 minus 8 is 172. So there we go. There's how we figure out that one. Okay, another example. An airplane is traveling 550 kilometers per hour on a heading of, or at, means the same thing, north 32 degrees west, and encounters a 80 kilometer per hour wind heading from south 11 degrees west. Notice the from is different, and that's why I underlined it. Determine the resultant ground velocity of the plane. Okay, so let me draw an example of what I'm talking about here. Okay, let's say this is headed north. So my original vector north 32 degrees west is traveling 550 kilometers per hour. So I'm going to draw a vector approximately. There's my airplane. And this is an angle of 32 degrees northwest. North 32 degrees west. Okay, let me draw another vector. This one says from south 11 degrees west. So that means we'd still draw a line, south 11 degrees west. So let's say it's this line. But however, the vector's head goes towards the origin. That's what the word from means. So this is 11 degrees. So what we want to do is we want to find the resultant. Now what you want to do is you want to draw the resultant so that it's coming from the origin. So we're going to take the 11 and we're going to move that vector up here, like so. So this is going to be our wind. And now I'm going to draw my resultant. If you don't draw your resultant coming from the origin, then it just might require you to move some things and work some values out. Okay, so the thing is, you know some pieces of information about this. You know this angle is 11 degrees down here, and this one's 32 degrees right here. So the angle in between right here is 180 minus 32 minus 11, which turns out to be 137 degrees. Due to Z pattern, this angle inside here is also 137 degrees. So now I can figure out my resultant using cosine law again. This one required us to find a little bit more information. But remember, you can always use your properties that you've seen before in order to find out angles. Okay. So using my calculator, I get this as about 610.9 kilometers per hour. Okay. I'm going to find this angle inside here. I'll call it theta. So sine theta is opposite the length of 80. Sine of 137 degrees is opposite the length of 610.9 approximately. So don't forget about the dot above the equal sign. Again, this is an example of a sine law, but it does not include an ambiguous case, so I'm just going to work it out. And I get approximately 5 degrees. So, let's write a concluding statement. Therefore, a resultant ground velocity is about 610.9 kilometers per hour. The direction, because that angle is 5 degrees from 32 degrees, is north 27 degrees west. And there we go. That's how you work out that resultant ground velocity. Something to note, some of you may have been taught how to add vectors using what are called horizontal and vertical components. We're going to talk about that more so in lesson 6.5. You can use that as an option, but it is not actually the fastest way to do it. The fastest way is actually technically using this process here. Okay, so let's try another problem. So, a mass is suspended from a ceiling, exerting a force of 5 newtons downwards by two chords that make angles of 45 degrees and 60 degrees with ceiling. Find the tension in the chords. So first of all, I'm going to draw a diagram. What this is saying. So there's some kind of box or mass being suspended, and right from this mass, you're exerting a force of 5 newtons downwards. The tension in the chords go into the ceiling because it's holding it in place. It's suspended. Let's say this is the 60 degrees and this one is the 45 degrees. Well, you'll notice right now these forces, all of these vectors, are actually headed in opposite directions from each other, or away from each other. This is not in a state of equilibrium. So what we need to do is we need to rearrange these vectors so that they are in a state of equilibrium in order to calculate anything. So we have that 5 Newton force downwards. We have one of the vectors going up into the ceiling like this in this direction, and we have another one going in this direction. I'm going to draw some dotted lines here and some specific spots. So I already knew this angle from the dotted line was 45 degrees from the horizontal, and this angle was 60 degrees right here from the horizontal. So that means I can figure out other lengths or other angles. So this one on the inside is 60 degrees due to the Z pattern. I could therefore figure out this angle right here is 30 degrees, and this angle inside is 45 degrees. So because of this, I can now figure out what the tensions are. So I can figure out one tension. Let's call this vector A, and let's call this vector B. So what I can do is I can set up a ratio here. So the magnitude of A is opposite the angle of sine of 45 degrees. The magnitude of B is opposite the angle of 30 degrees. And the 5 Newton force is opposite sine of 105 degrees. So all I can do in order to find A, its magnitude, that's sine of 145 degrees times 5 divided by sine 105. I work that out as 3.7 newtons. And likewise to find vector B, this is just the sine 30 degrees times the 5 newtons over the sine 105. Which turns out to be 2.6 newtons. Just because the lengths show something different doesn't mean which one's stronger or more intense. Okay, so therefore, the tension in the chords is 3.7 newtons and 2.6 newtons. You already know the directions technically just by looking at where they're headed. So no need to give directions. When they're just asking for tension, they're just asking for magnitudes. So one last thing to note. 3 vectors can only be in a state of equilibrium if 2 of the vectors' magnitudes add up to at least the magnitude of the largest vector. So in our first example, we actually have a triangle drawn. We find the vector u is a magnitude of 5.5, v is 4.5, and w is actually less than the addition of those two, so 7.5. Whereas this one, the vector u is 3.5, the vector v is 4, and the vector w is also 7.5. Those two values actually add up to be equal to w. So this is what we call the triangle law. The magnitude of u plus the magnitude of v, when added together, has to be greater than or equal to the magnitude of w. And this will always tell you the state of equilibrium for any three vectors. And thus concludes lesson 6.4.